Welcome to Chapter 1 Subskills for Trigonometry. In this video, we are going to work on operations on fractions, solving linear equations, one example of graphing a line, solving proportions, simplifying expressions with square roots, the Pythagorean theorem, and inequalities in one variable and interval notation. Let's go ahead and get started. We're first going to warm up with a few fraction problems. So 1a is 2/3 minus 4/5. Remember to add or subtract fractions, we need to find a common denominator. So for 2/3 minus 4/5, we need the denominator to be the same, but right now 2/3 has a denominator of 3 and 4/5 has a denominator of 5. So we need to think of a multiple of 3 that is also a multiple of 5. So one strategy is that you can count by the larger denominator. So if I count by 5s, I just count by 5s until I find a number that 3 also goes into evenly. So 5, 3 does not go into 5. 10, 3 does not go into 10. 15, 3 does go into 15. So therefore, I'm going to want to write each of my fractions with a denominator of 15. So now the question is how do I find an equivalent fraction of 2/3, but with a denominator of 15? And what the way we can change a fraction without changing the size of that fraction, or we can change the way it looks, but not the size, is we can multiply top and bottom by the same number. So 3 times what gives me that 15? 3 times 5. So now I can multiply top and bottom of this fraction by 5. Now I have 2 times 5 is 10. So 10/15 is equivalent to 2/3. I will do the same on the right-hand side. 5 goes into 15 3 times, so I multiply top and bottom of 4/5 by 3. 4 times 3 is 12. Now I go ahead and do that subtraction. 10 minus 12 is -2, and the denominator will stay the same. The reason is the denominator tells me the size of the piece. So I have 10 pieces, I subtract 12 of those pieces, so I have -2 of those pieces. Those pieces are 15ths. And we could either leave the negative up top, but it's common to put the negative out in front. The one place we do not want to leave a negative is in the denominator. So our answer is -2/15. Moving on to multiplication of fractions. So now we have 2/3 times 5/8. With multiplication, we no longer need common denominators. We can simply multiply straight across. So one option is just to first and foremost multiply straight across. 2 times 5 is 10. 3 times 8 is 24. And now we have to be sure to reduce this. So 10 and 24 can both be divided by 2 evenly. So we divide top and bottom by 2, and we get 10 divided by 2 is 5, 24 divided by 2 is 12. So our answer is 5/12. I do want to show an alternate strategy, which will be more helpful when we get to multiplying rational expressions later in this semester. If we have 2/3 times 5/8, one very helpful strategy is to reduce before we continue on. And this is a nice strategy that works as long as we are multiplying fractions or rational expressions. So this reducing first is only an option when you're multiplying. So what we can do is we can see anything on the top can reduce with anything on the bottom. So since 2 and 8 can both be divided evenly by 2, we can go ahead and do that. So we go 2 divided by 2 is 1, 8 divided by 2 is 4. Now we continue and multiply straight across, just like we did before. 1 times 5 is 5, and 3 times 4 is 12. Notice we get the same answer either way. Now, these numbers are relatively small, so in this case, either way is totally a viable option. However, when we're dealing with numbers or expressions that are more complicated, this strategy of reducing first is key because we're making things smaller before we make them big. And let's go on to 1C. Now we have 2/3 divided by 4/15. If you prefer, it is an option to just rewrite that using the more elementary division symbol. So we could rewrite that as 2/3 divided by 4/15. Now, it's always an option to rewrite it using this step, but eventually we may want to try and skip that step. Now, the rule for dividing fractions is one strategy for dividing fractions is we can flip the second fraction and multiply. So we can change that into 2/3 times 15/4. Now I'll go ahead and see if we can reduce first. So 2 and 4 can both be reduced by 2. So we can go 2 divided by 2 is 1, 4 divided by 2 is 2. Similarly, 3 and 15 can both be reduced by 3. So I will divide them both by 3. 15 divided by 3 is 5, and 3 divided by 3 is 1. Now I'm ready to multiply straight across. 1 times 5 is 5, and 1 times 2 is 2. So therefore, we get 5/2. Now, eventually, it will be a nice tool to be able to turn this straight into, if we look at the original problem, just go 2/3, and then we multiply by the reciprocal of the bottom. So we just flip the bottom fraction 15/4, and you'll see that gets us here, right where we were over there. Okay, let's go ahead and look at solving linear equations. These equations are linear because the variable x doesn't have a power on it. So there's no x squared or x to the 4th power. Also, we don't have the square root of x. Now, when we're trying to solve for a variable, we're trying to find out what it equals. And to find out what it equals is we want the variable alone on one side of the equation. So first of all, I like to identify where that equal sign is, and I'm trying to get over on this left-hand side, I'm trying to get only an x. So the first thing we can do is cancel out any adding and subtracting. We can add 1 to both sides, and we get 7x equals -21. Since we have -22 and a +1, those are actually canceling out, but we're left. Now, 7x equals negative 21. We can either do this mentally, or we can ask ourselves, what is the operation between 7 and x? Well, that's multiplication. So the opposite operation will be dividing. So now to get the x by itself, we could divide both sides by 7 to get our final answer of x equals negative 3. Remember, a negative divided by a positive is always a negative. Now, this is optional, but you could go ahead and check to make sure that's true. We could go and plug in the x into the original equation. So we have 7x minus 1 equals negative 22. We could plug in x is negative 3 and see if it does in fact equal negative 22. So 7 times negative 3 is negative 21 minus 1. Does that equal negative 22? Well, if we're down at negative 21 and then we subtract one more, we go even lower to negative 22. And so negative 22 does in fact equal negative 22. And this is optional to check your answer, but it's nice to see what this answer of x equals negative 3 actually means. Okay, now we have a little bit more complicated linear equation. We have 3y minus 5 equals 3 plus 7y plus 40. Now, we need to first see if we can simplify either side of the equation. So on the left-hand side, we have 3y minus 5. Those are not like terms since the 3 has a y with it, but the negative 5 does not. On the right, we have 3 plus 7y plus 40. Now on that right-hand side, we can see that 3 is just a regular number 3, and 40 is also just that regular number 40. So those are like terms and can be added together. So we combine like terms on the right to get 43 plus 7y. On the left, I will just copy down 3y minus 5. Now, this linear equation is a little different because we have y's on both sides of the equal sign. So the first thing we want to do is get all of the y's to both sides. We have a choice. We can either subtract 3y from both sides, or we can subtract 7y from both sides. I will go ahead and subtract 3y from both sides, only so we are left with a positive number in front of the y, or a positive coefficient for y. So on the left, the 3 y's cancel out, and we are left with negative 5. On the right, we bring down the 43, and we have 7y minus 3y. And since we get a positive 4, or when 7 minus 3 is a positive 4, we will write plus 4y. Now we have all of the y's on one side, on the right-hand side in this case, and we're trying to get rid of all the other numbers around the y. So the first thing we will do is subtract 43 from both sides. And since we have negative 5 minus 43, that's negatives and more negatives, we're going to get negative 48 equals 4y. And to cancel out the multiplying by 4, we will go ahead and divide both sides by 4. Thus, we get negative 12 equals y. Now, at this step up here, if you would have subtracted 7y from both sides instead, your work will look different, but your final answer will in fact be the same. So that is a brief review of solving linear equations. Now we're going to look at an equation. It's still linear in form, but now we have two variables. So we have x minus 3y equals 0, and we're going to try and graph this line. Here, there is not just one solution. There's actually infinitely many solutions because different x values will give us different y values that will satisfy this equation. So one strategy is to come up with multiple points that will work to satisfy this equation. So we could just make a table of x and y values and try and find x and y values that will satisfy this equation. So we might try something like 1, 1. If x is 1 and y is 1, and let's see. Well, 1 minus 3 times 1, I'm plugging in 1 for x and 1 for y. And we want to see, does that equal 0? Well, we multiply first because order of operations requires us to multiply before we add or subtract. So 3 times 1 is 3. 1 minus 3 will not equal 0. So that means the point 1, 1 is not on the graph. Let's try some other numbers. How about if we tried 0 for x? Okay, so if x is 0, let's see what y would have to be. Well, if we have 0 minus 3 times something, but we want it to equal 0, we're going to need 0 minus 0. So 3 times 0 will allow us to get that 0 minus 0 equals 0. So let's move over to our graph real quick. I'm going to set it up. And I notice I have a grid. If you do have graph paper or even line paper, it's good to draw your axes on the grid. So notice I'm going through the dots. And I will label my tick marks. So 1, 2, 3, 4, 5. And I have my horizontal axis is my x-axis, my vertical axis is my y-axis. So the first point we found was when x is 0 and y is 0, that point is on the graph. And so now we need to play with another point that would be on the graph. So we can explore. Now you may play with different x and y values and push pause if you want to try and come up with any. But another thing, if I'm trying to think, okay, one number minus another number has to equal 0, maybe I could come up with like 2 minus 2, or in this case 3 minus 3 might be easier. So let's give that a try. What if we have x is 3, then what does y need to be so that this ends up being 3 minus 3? Well, what do we need to put in for y to get this second term here to be a 3? And that's going to be a 1. So when x is 3 and y is 1, let's check it out. 3 minus 3 times 1 is 3, and that does in fact equal 0. So when I plot the point 3, 1, the X value goes side to side. And or here, let's just real quick. If I plot an XY coordinate, the X value takes me side to side, right is positive, left is negative, and the Y value takes me up and down. Up is positive and down is negative. So the coordinate 3, 1 will go right 3, up 1, and then I put a point. Now, if I happen to know that this is in fact a line, right here, I can go ahead and draw a straight line through it. We can also notice the pattern. Notice I'm going up 3 over 1, so I could continue that pattern. Up 3 over 1. And then backwards would be down 3, left 1. Now, this is just one strategy of trying to come up with X and Y values that satisfy this equation. And this works as long as you can mentally come up with a couple of those coordinates. So you need at least 2 coordinates to be able to determine a unique line. Now, there's also slope-intercept form. And this is more of a review. It's pretty involved, but just so you know, or just so you've seen it, we could also use the form y equals mx plus b. So if this is one strategy that you like, then you could solve for y. So if I take that equation, x minus 3y equals 0, and I want to solve for y, the first step is subtract x from both sides. So the x's cancel on the left, and I get negative 3y equals negative x. Now I can divide both sides by negative 3. Now this gives me the y is by itself, y equals, and I want a number in front of x. So if I put a 1 or a negative 1 in front of x, now I can say, okay, 1 over 3, but a negative divided by a negative is a positive. So I get y equals 1/3 x. And if we do this method, the first step is, what is b? What's being added over here? Well, nothing. So we say, okay, well, b is 0. So that means my y-intercept is 0. I start at the origin, that's this point here. And then the second step is m, or my slope, is 1/3. And so from my y-intercept, I'm going to use that as my rise over run, and I'll go up 1 over 3. So from that y-intercept of 0, I go up 1 over 3, up 1 over 3. Now, this method down here is a little more involved. So if you are interested in understanding this more completely, it will require a little bit more time. And you would be looking, you would want to look for slope-intercept form of a line. Okay, but I just wanted to quickly recap that if any of you have seen that before and wanted to see how you would graph it in that, using that method. Let's move on. Next, we're going to work on solving proportions. So first, this first problem, 3 over x equals 7 over 24. This can be solved mentally. And I would encourage you to push pause and see if you can reason through that solving. I'll go ahead and focus on the algebraic approach, since that's going to be more relevant for trigonometry. So we have 3 over x equals 7/28. One strategy for solving proportions is cross multiplying. So what I mean by that is we can multiply across the diagonals. So 7 times x, or 7x, will equal 3 times 28. So notice the 7 and the x are diagonal from one another, and the 3 and the 28 are diagonal from one another. So now we can multiply 3 times 28 to get 84. And now we have 7x equals 84, which is a very simple equation. Now we just divide both sides by 7, and we have it, x equals 12. And if we did want to check that, we could see 3/12 supposedly is supposed to equal 7/28. Well, let's reduce each of those. We can reduce those both by 3. 3 divided by 3 is 1, 12 divided by 3 is 4. And on the right, we can reduce those by 7. 7 divided by 7 is 1, and 28 divided by 7 is 4. And look, we have 1/4 equals 1/4. And I do want to point out that if you would have noticed originally when you looked at this problem that 7/28 could be reduced, you can reduce it at any point in time, and it will actually make the math a lot easier. Let's go ahead with a little bit more sophisticated proportion. Now we have x plus 2 all over x equals 7/11. Now, when I look at this, this is not something I can mentally strategize. I have to have a technique. So this is where that cross multiplication is very powerful. Again, we're going to multiply across the diagonals. So I will get, when I multiply, I can multiply 7 times x and get 7x. I need to be careful when I multiply 11 by x plus 2. I need to make sure I'm multiplying the 11 by the entire expression, x plus 2. So one strategy is to use parentheses around that x plus 2 and get 11 times that quantity, x plus 2. And in doing so, we will make sure that we distribute this 11 and multiply the 11 by x, and we'll multiply the 11 by 2. And this will give us this next equation, 7x equals 11x plus 22. Now we can, or again, we have variables on both sides of our equation. So we can subtract 7x from both sides, or we can subtract 11x from both sides. In this case, it's advantageous to go ahead and subtract the 11x from both sides, since this right-hand side has another number, a constant, whereas the left-hand side doesn't. So it will just mean less steps. However, we could instead subtract 7x from both sides. We just have to be careful with the placement of that equal sign. So 7x minus 11x is negative 4x. And on the right, the 11x's cancel, and we get 22. Now we will divide both sides by negative 4, keeping that sign the same, because we're looking for a positive 1x. And so we get x equals 22 over 4 with a negative. And notice 22/4 can be reduced by 2. So if I divide the top by 2 and the bottom by 2, my final answer will be x equals a negative 11 halves. And that's it. Okay, now we are going to get into simplifying radical, or actually just simplifying square roots. So there are a couple different strategies for this. The first thing that's really important when you're looking at square roots is to think of what are our perfect squares, or what are some square roots that come out nice. So we have the square root of 4 is 2, since 2 times 2 is 4. The square root of 9 is 3, since 3 times 3 is 9. And we could keep going with that. We could do the square root of 16 is 4, and the square root of 25 is 5. This is usually the ones I write out most commonly, but of course you could add to that list as if you are dealing with bigger numbers. So one strategy for simplifying square root of 12 is to determine if any of these perfect squares, like 4 is a perfect square, 9 is a perfect square, if any of these perfect squares goes into 12 evenly. So does 4 go into 12 evenly? Yes, because 12 is divisible by 4. So I can rewrite the square root of 12 as the square root of 4 times the square root of 3. And I like to put that perfect square in front. So I have square root of 12 is the square root of 4 times the square root of 3. And now I can evaluate the square root of 4, and the square root of 4 is just regular 2. So now I have 2 radical 3. And this here is the simplified version of the square root of 12. And this is where it's nice to evaluate. Sometimes it's nice to just kind of check it out on a calculator. And this is more just a check. If I put in the calculator square root of 12. Now, some calculators these days will actually tell you it's 2 rad 3. But if I make it as a decimal, I get approximately 3.464 and then some other digits. Keeps going. But if I also put in 2 times the square root of 3, it will also give me that exact same number there, or that exact same approximation. So here we see that the calculator shows us that they are giving us those same decimal approximations. I do want to also include a different strategy, which is using factor trees. So if I take this 12 and I try and factor it out, so I could say, okay, well, what 2 numbers multiply to 12? And if I'm using factor trees, I'm not only focusing on these. I can say 2 times 6. Whereas over here, using this original method, if I separated it into rad 2 times rad 6, that is not helpful at all, because rad 2 is not a whole number, and the square root of 6 is not a whole number. So that is not helpful over here. For factor trees, it doesn't matter how you break it down. You just keep going until you get into primes. So I can factor 6 into 2 and 3. And now if I want to figure out how do I rewrite square root of 12, is any pairs come out once out of the square root and any individual numbers stay inside the square root. Okay, so this is just rewriting your radical in terms of a perfect square times any other number, versus this is using factor trees. Okay, For B, now we have the square root of 7, or I'm sorry, the square root of 5 divided by the square root of 7. One of the standards, it's kind of, it's not a steadfast rule, but one of the agreed upon standards is we don't leave our answers with a square root in the denominator. Now, some textbooks and professors are softening on that rule, but a lot of texts require us to simplify further so that we do not have a radical in the square root. I'm sorry, we do not have a square root or a radical in the denominator. So again, we can multiply or divide top and bottom by the same quantity. And so we want to think, what could we multiply rad 7 by to give us a whole number, or a number that's no longer in a square root? And what it is we can actually multiply top and bottom by rad 7. And let's observe. So we're multiplying top and bottom by the radical in the denominator. Let's see what we get. On the top, square root of 5 times square root of 7, we get square root of 35. So it is acceptable to multiply two square roots, even if the numbers are not the same. Now we get square root of 7 times square root of 7. Well, that's square root of 49. But what is the square root of 49? It's regular 7. Because 7 times 7 is 49. And you could also keep going if you wanted to on the list. Notice we already have our square root of 4, square root of 9, square root of 16, square root of 25. We could keep going with that. Square root of 36 is 6, and square root of 49 is 7. And so this, if we have square root of 5 divided by square root of 7, that can be simplified as square root of 35 divided by 7. And here, C. 3 divided by the square root of 18. Now we have lots of choices as far as the order goes, but what I will go ahead and do is I'm going to simplify the square root of 18 first. So to do that, I'm going to think, okay, what perfect square goes into 18 evenly? So does 4 go into 18 evenly? Nope. Does 9 go into 18 evenly? Yes. So I will write it as square root of 9 times square root of 2, because 9 times 2 is 18. Now the 3 on the top just hangs out for a bit. And now I have the square root of 9 is 3, and my 2 is still in the radical. Now, again, the order in which we simplify, there's lots of options, but I'll go ahead and try and get the radical out of the denominator. So notice the square root of 2 is in the denominator, and that's the problem. The 3 in the denominator is not a problem. So I will go ahead and just multiply top and bottom by rad 2, and let's see what we get. So on top we have 3 rad 2. On the bottom we have 3 times rad 4. 3 times rad 4, which is the same as 3 times 2, or 6. So we have 3 rad 2 over 6. Since everything here is multiplying and dividing, we can go ahead and reduce the 3 and the 6. So, and also the 3 and the 6 are both outside the square root. So notice the 2 and the 6 cannot be reduced because the 2 is in the square root, the 6 is not. but the 3 and the 6 both are outside the square root, so I can reduce them both by 3. 3 divided by 3 is 1, 6 divided by 3 is 2. And the final answer for this problem is rad 2 over 2. And if you would have noticed that the 3's could reduce here, that would have been another option. There's a lot of options as far as the order in which you reduce. Notice here, I could not reduce right away. The 3 in the original problem, 3 divided by the square root of 18, I could not reduce those right away because the 3 is not in the square root and the 18 is. But here at this level where it was 3 divided by 3 rad 2, at this stage, if I would have noticed the 3's could cancel, that would have been an option. Okay, last but not least here for the radicals for now, we have 3 rad 5, that entire quantity squared. Now, I will show this 2 different ways just so you can see. One option is to just think, okay, what does that mean to square something? So I could just multiply 3 rad 5 times itself, times another 3 rad 5. That's one option. So 3 times 3 is 9. Rad 5 times rad 5 is rad 25, or the square root of 25 is 5. So I get 9 times 5, which equals 45. As soon as you're ready to see that the rad 5 times another rad 5 just gives you a regular 5 and skip, that is great. Some people feel comfortable with that sooner than others. I'll go ahead and show you another method, and that is bringing in the square. And that actually works because kind of our structure of math, we have, I love this little list right here, order of operations, and it gets with solving. There's a lot of patterns in this, but notice the square is a power, and in between the 3 and the rad 5 is multiplication. And since these are neighbors, power and multiplication, we can go ahead and just bring in the power to each factor. So we get 3 squared times rad 5 squared. And here we get 9. We could either get the square root of 25, or we can see that the square and the square root are inverse operations of one another, and they cancel out. So we get 9 times 5 is 45. So either method here works great. Either way, we get 45. Now, moving on, we have the Pythagorean theorem. And we're going to have different right triangles. So it's very important to know that this Pythagorean theorem only works for right triangles. So I'll go ahead and draw an example of a right triangle. And if we make, denote that that's a right triangle, C is the right angle, which means that little c is going to be the side opposite the right angle, and we call that the hypotenuse. If I put angle A up here, then the side opposite angle A will be side A. And notice I'm using capital letters for the angles and lowercase letters for the sides. So opposite angle B is side B. And we have that A squared plus B squared equals C squared. So let's go ahead and apply this. We can use this a squared plus b squared equals c squared, but we're going to plug in a is radical 2, then we need to square it. B is 4, we need to square it. And then it's going to equal c squared. So again, the square and the square root on 2 will cancel out. And so on the first term there, we're just left with 2. Or similarly, we could square the 2 and get the square root of 4, which is still 2. Now, 4 squared is 4 times 4, or 16. And that will still equal c squared. So we're just bringing down all of the quantities. Bring down the equal sign, bring down that c squared. Now, these are like terms. So 2 plus 16 is 18. And that still equals c squared. So now we're trying to solve for the missing side of this right triangle. And so we're trying to get c all the way by itself. So in order to do, we need to do an inverse operation of squared, and that's going to be square root. So we will do the square root of both sides. Technically, we need a plus or minus, but when we're solving for the length of a side of a triangle, we're only taking the positive. So we get that c is the square root of 18. And we have to decide, can we simplify that? So just like when we learned how to reduce fractions, you learn how to reduce fractions once, but then from then on, you have to look at your answer and make sure your fractions are simplified. The same with square roots. Anytime we're dealing with square roots, we have to make sure our final answer is simplified. So we look at our perfect squares. Does 4 go into 18? Nope. Does 9 go into 18? Yes. So we write that as rad 9 times rad 2, or 3 rad 2. And so we found that the hypotenuse is 3 rad 2 if the legs were rad 2 and 4. Okay, and for B, part B, we have A equals 2 rad 3 and C equals 5. Notice now they're giving us one leg and the hypotenuse, and we needed to find the other leg. So using that formula, a squared plus b squared equals c squared, we're going to plug it in. So plug in A is 2 rad 3. Be careful to make sure we square the whole thing. So I'll put the 2 rad 3 in parentheses, then square that. Plus b squared equals 5 squared. So now we'll square the 2 to get 4. Actually, I'll write that out. We'll get 2 squared plus rad 3 squared plus b squared equals 5 squared is 25. And so we get 4, on that first term, we get 4 times rad 9, or 3. 4 times 3 is 12. So I'll write 12 plus b squared equals 25. Now we're trying to get the b squared by itself. So we will go ahead and subtract 12 from both sides, since the 25 and the 12 are not on the same side of the equal sign. So subtract 12 from both sides, and we get b squared equals 13. Last step, to cancel out a square root, to cancel out the square on b, we can take the square root of both sides, and we get that b is the positive square root of 13, since it's the length of the side of a triangle. And there we have it. We found that if one leg is 2 rad 3 and the hypotenuse is 5, the missing leg would be rad 13. All right, for our last subskill that we're going to work on for now, we have inequalities. We can write that with set builder notation. So this, when we're comparing something like x is greater than 2, or down here it might be y is less than or equal to 3. So our a and our b are actual numbers, where here, actually I'll stick with x. We could do x is less than or equal to 3. X is our variable, but a and b would actually be numbers. And maybe down below, I'll pick one of these. We could even have something like 2 is less than x is less than or equal to 3. So that's what these will look like in practice. So we can verbalize it, the set of real numbers greater than a, or x is, in this case, x is greater than 2. Then when we graph it, now there are 2 different ways to graph inequalities. One, it's common to use open circles for less than or greater than, and versus closed circles for less than or equal to or greater than or equal to. Well, similarly, we can use, just like for the open circles, we could use parentheses instead, and just like the closed circle, we could use brackets instead. So you can always push pause and take a moment to understand this a little further. But I'll keep going. One thing I do, and one other piece that I do want to point out is, notice if infinity or negative infinity is ever used, it's always parentheses. So we never use brackets with positive or negative infinity. So let's go ahead and see this in practice. Now, interval, or we're given this graph. So we're given, it's shaded in to the left of 2, and then there's a bracket on 2. So let's first look at our interval notation. Now, a couple rules with interval notation is you always list the quantities least to greatest. So on a horizontal number line, it means left to right. For this, okay, what's farthest to the left? Where are we starting? Well, there's an arrow, so it continues. So we're actually going from negative infinity and ending at 2. So interval notation is almost like start to end. Where do we start? Where do we end? So we start at negative infinity, we end at 2. Now we need brackets or parentheses around it. So because it's an infinity or negative infinity, it will have to be a parenthesis on the left. But because there's a bracket on the graph, it means there will be a bracket on the 2 in interval notation. And so that's negative infinity to 2 with a parenthesis on the left and a bracket on the right. Moving on to set builder notation. First, let's work on the inequality part. So the graph that we see, the blue part is x, or whatever variable we choose. I'll go ahead with x. So if we choose to use x, and then we have to decide, is all of these numbers over here, the shaded in part, are those numbers less than 2 or bigger than 2? Well, 0 is less than 2, right? All of these numbers over here, negatives, are all less than 2. So is 1. So x is less than 2, but the bracket is going to include 2. So we show that by x is less than or equal to 2. And that is an inequality. But to put it in set builder notation, we put the variable in front of it. So we're using x as the variable with a vertical line. And then curly brackets around the whole thing. So the way this reads is all real numbers x such that x is less than or equal to 2. All right, for the next one, we're given the interval notation of negative or bracket 11 to infinity. So let's go ahead and graph this. So we're going to need a number line. And if you want, you can include 0, but you do not have to. I'll go ahead and start at 9 and see how far I get. So I did 9, 10, 11, 12, 13. One thing that's important is I tried to make my tick marks evenly spaced and my numbers counting, in this case, by ones. So let's go ahead. Now I'm going to do a bracket at 11 and shade in from 11 to infinity. So first I'll go ahead and shade to the right from 11 to infinity. And now I'll put a bracket on 11. Similarly, I could have done a closed circle. This would also be an acceptable graph. I'll go ahead and leave it as a bracket because it goes nicely with interval notation. And now we need to write an inequality and put it into set builder notation. So notice again, I'll use x again, and x has to be what's shaded. So is x, are these values over here, are those bigger than 11 or less than 11? Well, 12, 13, those are definitely bigger. So x is greater than 11, but because of the bracket or a closed circle, we would say x is greater than or equal to 11. Again, the set builder notation, just we get a vertical line, the variable, and curly brackets around the whole thing. Last one here, we have all real numbers y such that negative 2.5 is less than or equal to y, which is less than 2.5. So let's go ahead. I'll work kind of backwards on this. Let's go from the interval notation. No, I'll go to the graph. I like to kind of visualize it on the graph and then go to interval notation. So again, I will draw my horizontal line. In this case, I will definitely want to include 0 since it's in between the two numbers. And I have a choice. I could either count by ones and then carefully place my 2.5 and negative 2.5, or I could go ahead and label my 2.5 and negative 2.5, as long as it's evenly spaced. I'll go ahead with this. Now, anytime we have an inequality where you have a variable in between two numbers, as long as the symbols are both facing the same direction, and it is true that this negative 2.5 is less than the 2.5, then it's simply saying numbers in between negative 2.5 and 2.5. So I could go ahead and just shade in between them. And then I need to be careful with my parentheses and brackets. So I need to frame this. I could, because it is, my y is greater than or equal to negative 2.5, because of this little line here, I'm going to get a bracket at negative 2.5. And because there is no little line comparing to positive 2.5, I will get a parenthesis. And so that is the graph from negative 2.5 to 2.5 with a bracket on the left and a parenthesis on the right. Similarly, I like to just show if you prefer open and closed circles, that would also be equivalent to a closed circle on the left and an open circle on the right. Again, I will leave it as a bracket and parenthesis. And again, you can see the interval notation really comes directly from the graph using those brackets and parentheses. So on looking at that graph, where do I start? Negative 2.5, comma, where do I end? Positive 2.5. On the left, it's in the negative 2.5 is included, so I get a bracket. On the right, the positive 2.5 is not included, so it's a parenthesis. And there we have it. So we are now done with our subskills for chapter 1.